So we're going to do a little bit more here with section 5.3, still with the shell method. However, in this case, we are going to look at a function whose height is the difference between an f of x and a g of x. And this could also be done in the opposite way too with curves, but that is the only difference, and that's what I want people to see here, is that you still have shells, they still have some, one of their dimensions is still 2 pi r, where r is, in this case, x. It's just the height of it is a bit different. So we'll take a look at an example. We have a region bounded by the curve. We're basically just going to do some setup here because that is the hardest part. So you can see the region, it's been shaded, and this is going to be revolved around the y-axis. So if I want to, I could just kind of make a basic idea of what this is going to look like. It's going to head down, it's going to go this way. Ooh, okay. And and then we are going to notice that, and I'll put some more information on it, but we're looking at shells that are this direction. It's going to be like over here, and then we are taking that shell, it's getting revolved around, bottom of the shell here, and around, you know, something like this. So that's what we want to be thinking about. Wow, I'm making a very detailed shell. Didn't even know I was going to do that. All right, so that's a bunch of those from in all the way out is what needs to be added up. So we can make some notes if we want on this picture that was drawn here. We see pretty straightforward that we have this is x equals 9. Here we have y equals 6. And then you can see that we also have this curved function, which is also down here, but we're not using that part. And that is the y equals 3x over x minus 1. So when we think about these shells, we want to understand here that the volume of, in this case, this example here, is the fact that we're going to be integrating this from where it begins, which you can see it starts right here and it ends right here. So we're integrating this, and we're only focusing on that right hand side, from 2 to 9. So that's where all the shells are starting and ending, 2 to 9. Then if you were to take this shell that I've created here and you were to cut it in the middle and stretch it out, you're going to have one big long rectangle with depth, and of course that depth is going to be some dx because that's how, you know, thick it is. And you're going to have 2 pi, and then you still want to remember is that the radius of whatever this shell is from here to here, and that is just some x value. That's wherever you are, so that's x. And then of course the big part of this is the height of it, and the height of each shell is from here to here. So you can see that whatever that distance in between, because this is not, we're not hitting the x-axis here, we're just going between those two functions, is that you're going to take 6 and then you're going to subtract whatever is this value down here, and that's on that function 3x divided by x minus 1. So now let's see what happens when we rotate this around a different line. So now this is the same exact thing, but we're going to rotate it around the line x equals 2. So that is, you can see this line right here. So a couple things to notice, okay, is we still have the same thing that's being rotated. In this case, I have to kind of think about this, but it's going to start, the reflection's going to look like this. So it's just going to start and it's going to go down. But notice that's going to happen right at the x equals 2. So now we have something like this, and it looks like 2 to 9 is 7. So 1, 2, 3, 4, 5, 6, 7. So it would end right here. Okay. Sorry about that. Okay. So what we have is, again, still very, very similar shells. Very similar shells. Still here. Trying to reflect it, so something over here. And we have these shells. But I want you to notice that there is something that's changed. And it's because these shells are not as big anymore, because the reflection is not on the other side of the y-axis, it's on the line x equals 2. So although the height of this is still the same, there's no change in the height. The big change, which some of you probably see, is the radius. So the radius of this has changed. And it's changed because it is smaller. And it's smaller because it is now being, the shape's been rotated around x equals 2. And so that's the key thing, is that what this has done is this has shrunk the radius. And so we just need to show that, like if you were to peel this open, and again, look at that length of this rectangle, it's going to be 2 pi times not x, but I'll show you. Let me start this here. So we have 2 pi, that is the same. We're still going from 2 to 9. That has not changed. I mean, that piece is still integrated from 2 to 9. That's where all the shells are going to be. Like I said, the height you can tell is no different. So we're still going to have this height. The only difference is this piece right here. Instead of x, let me find a different color. The radius of this is from here now to here. So notice it goes from here to here. So out here is some x. That's wherever you are along the x-axis. And here is 2. So this radius now, if you needed to find that distance, you'd have to go, well, where am I? Well, I'm out at x somewhere. And if I subtract 2, that's going to give you that distance. And so that is the radius, and therefore the piece of information that you need for the length of your shell. So this would be the setup for this problem. So for the last thing that we're doing, notice the only difference is we're still using the shell method, but we have f of y minus g of y. So now we might have curves instead of functions. And so we're thinking about the shells doing this idea. Coffee can. So doing this idea where we might have a curve and then another curve. And so we might have to do some subtraction of the values in order to get kind of, you know, one piece of the cylinder, you know, the rectangle that's created. So let's take a look. So we have this region. We've got x equals square root of y. We've got a line, and then we've got a horizontal line as well. So we have y equals 1. We have our line here, y equals -1/2 x plus 5. And up here, x equals square root y. So our job is to find the volume. We're still just going to do the setup here, just so these videos aren't 8 million hours long. You can also think about the fact that, oh, this is x equals square root y, which is the same as y equals x squared. Okay, so first thing we're going to do is revolve it around the x-axis. So actually, maybe I'll keep my color for the moment. So you can think about what that would look like if you were to reflect it. So you're going to have some piece that goes from here to here. So notice I'm just reflecting that, so I'm going to be at -1. And then you have a line, I'm just try to find some values. So it looks like I have 6, 2, so I'll have 6, -2, oh, 6, -2, not 6, -3, 6, negative 2. And all right, I'll do 4, 3, so I'll do 4, negative 3. Okay. And of course, an important point there is 2, 4, so I'll have 2, negative 4. Okay, so we have something that looks like this. And then of course the last piece is like a curved piece. So I'll do the best I can there. Kind of looks like that. Okay, so that's our rotation. That's the piece that's getting rotated. And so hopefully you can kind of see here what we are rotating and what that's going to look like. So let me get my red. Okay. So I'm going to have basically a piece like this, and that's going to come down, you know, and be down here somewhere. That'll be where it, and then it's, you know, it's going to look something like this, okay? So cut me some slack, something like this, you know, on the other side. Okay, so it's shells that have that shape. So that's the idea here. We want to be thinking about that. So things to pay attention to and things to notice is this means we're going to be following what you saw on the last slide. And notice you're always going to have this volume is going to be the 2 pi, as long as you know you're using shells, 2 pi. And then you need to have your radius. And I guess if I'm going to have my radius, then that's not going to be on the outside, so I'll just move this back. So radius here, because it's just around the y-axis, it's just going to be y. And that's because the radius of this shell that I've created, you're thinking of it like this. Oh my gosh, that is a really bad height, but that height there is y. I mean, it's just as high as you go, which is y. Now, in terms of this distance, well, that's what's getting you thinking that you're going from here to here. And that distance is the difference between two different functions. So you can see that y equals negative 1/2 x plus 5 is always on the right, and then your y equals x squared is on the left. However, these shells need to be in terms of y. So we already have one because we have x equals the square root of y. We would also need y minus 5 equals negative 1/2 x. And then if we multiply through by negative 2, that's going to give us a negative 2y plus 10 equals x. All right, so now we know what x is equal to. Okay, and even though you can see the boundaries there, remember that one option you have, if you're not sure where things are going to meet up, just set things equal to each other and you can find those points. So we can see that our graph here is starting at y equals 1 and is going up to y equals 4. So I mean, we can just see that from our graph. If you did want the intersection points, you could set the two functions equal to each other. So I'll do the y value. So negative 1/2 x plus 5 should equal x squared. So that'll give me x squared minus plus 1/2 x minus 5 if I bring everything to one side. If I don't like that, I could multiply through by 2. That would at least help me out. And then I could factor it, and that'll give me a 2x and x. I want to have a positive, so it looks like I'll have to do 2 and 5 and plus and minus. So that'll give us x equals 2 and x equals a negative 5/2. Well, this is not part of our interval here, so we just have x equals 2. So if x equals 2, then y is going to equal 4, so we get the 0.24. So that would have been this point up here. If we didn't have it, we could find it. And then we can see that at the bottom here, everything connects with y equals 1. So that's how we know we have, 1, 1, it looks like, and 1, 8. So again, you can always set things equal and figure out what points you need. For something this complicated, you're probably going to be given a graph, but it's always good to know how to do things. All right, so all we need now is to think about this idea of, like I said, this distance here. And we can see that no matter where we are, what shell we have this function on the right. So we'll have negative 1/2, nope, I want to have it in terms of y. So I'm going to use negative 2y plus 10, and then from that I need to subtract the other function in terms of y, which is just the square root of y, and then dy. So that's the whole thing for that one. That's the whole setup. Obviously you could multiply it out, you could rewrite like the square root of y, and then integrate and evaluate. These are all possibilities, but the setup is the toughest. Okay, so last one here. So now, very similar to kind of 2 problems back, we're taking the same exact thing, but we're just going to rotate it around the line y equals -4. So now we're down here, and you can see that what that's going to do is, not surprisingly, that's going to increase the radius, because instead of rotating around the y-axis, we're rotating around the y equals 4. But it doesn't affect this distance here. The only distance it changes is the distance from, basically the radius of what this shell is going to be. That's the only thing that has now changed. So instead of just being y, you can see that now it's actually y minus a -4, the radius of the shell. So y plus 4. So other than that, that's actually the only difference here. We can see we're still evaluating from 1 to 4. We still have, I'll just put it on the inside this time because it doesn't matter, 2 pi y. But again, now our radius is increased by 4. So you want to do y or x minus whatever that line of rotation is. So y plus 4. And then we have the distance here, which is the same as what we had before. So that was a -2y plus 10, subtract the square root of y. So that has not changed. So key thing here is just the rotation around the different line of axes changes your radius. So that's what this is affecting here. So again, it'd be a lot to multiply this out and do it. We're not going to do that, but know how to set these up, know how they change as well. So the last thing here are just a couple tips on how to choose which method you want to use or need to use for volume. So if your cross sections are taken perpendicular to the axis of rotation, you'll use either the disk or the washer method. If your cross sections are taken parallel to the axis of rotation, we use the shell method. So in this section, I just have the shell method going on, so you can take a look at your notes for the other disk and washer. So if we take a look back at one of our past examples using the shell method, what they mean by parallel, hopefully you can see that what's happening is we're looking at the fact that the cross section, this shell, is parallel, so that these two are in the same direction. What you'll notice with the washer method is that you might be rotating around something like this. So your rotation is like this, but your cross sections are like this. And that's what's telling you not the shell method, the washer or disk method. So again, I can show you on one of these as well. So notice again, in this case, we have our axis of rotation here is this line, but here is our cross section. So our cross sections are in the same direction as the axis of rotation. And so that parallelness is telling you the shell method. And so here is one of the problems we did in section 5.2. This used the disk method. And so what I want to show you here is you're looking at your cross section and you can see the cross section that we have. I have to find out where there we go. The cross section that I have is here, but that's perpendicular to what we're rotating around, which is the x-axis. So that is the difference. Notice that the cross section is in a different place. Now, we could also look at maybe one more example here. So like, again, in this situation, you've got your axis of rotation, which is the x-axis, axis of revolution. This is what we're revolving around, but yet your cross section is perpendicular to that. So in this case, we have the washer method, but it's disk or washer that you're going to be thinking about if you have that aspect of being perpendicular. And then notice on this one that it's the washer method because this axis of revolution, this x-axis, is not your boundary. It's not where the function essentially stops, because in this case you have a top function and a bottom function. That's the washer method. However, coming back to what I just mentioned over here, in this case it's the disk method because your boundary region here, your plane, is the x-axis. So the function goes from the function to the x-axis. And because of that, that's telling you disk method, not washer method. And that is section 5.3.